We've already worked a little bit with our Cartesian coordinates, but let's go ahead and return to it and formalize a couple definitions. So with our Cartesian coordinates, of course, we have our point defined by x, y, and z. So I've got a three-dimensional axis drawn here below. And we can draw our important unit vectors in our x, y, and z directions. So of course, let me make this a little thicker here. So we're going to have an x unit vector in our x direction, like this. So that's our u sub x, and a little hat for a unit vector. A unit vector in our y direction, like this, and a unit vector in our z direction, like this. And notice, because these are all mutually perpendicular, this satisfies the criteria for an orthogonal system. Now, of course, these three unit vectors could be at any point. They don't necessarily have to be at the origin. That just happens to be how I draw it here. A couple things about the limits on our three values that we're defining. So all three of our values in this case can be between negative and positive infinity. So for instance, our x can go all the way to negative infinity or all the way up to positive infinity. Same thing for our y, and same thing for our z. And so that kind of seems, basic. Why would we even need to state that? And we're going to see, of course, that's not going to be the case for our other two coordinate systems. We're going to have different limits on those values. Remember, we can define vectors. So if we have a vector A, we can write that as just, so let me write this up here. So we can write this with our angled brackets. So we can say we have some x component, some y component, and some z component. Alternatively, we could also write our A as being equal to ax times our unit vector in the x direction, plus ay times our unit vector in the y direction, plus az times our unit vector in the z direction. And then, of course, we have already seen our magnitude of A is just defined as the square root of our ax squared plus ay squared plus az squared. One thing I want to mention, at least briefly, it's in a later section of the textbook, section 2.5, and that is constant coordinate surfaces. And we'll kind of talk about these as we introduce each of our three coordinate systems, as opposed to looking at it at the end. But what this is, with our constant coordinate surfaces, we're basically saying if we set one of these three sort of variables equal to 1, what does the resulting surface look like? So for instance, let's say we set our y equal to some value. So what we're going to get from that is an infinite plane that is sort of parallel to our x-axis there. Let me see if I can draw that a little bit better. So we get something that looks like this, and of course I can only draw a section of this infinite plane, not all of it, but it would extend up, down, back towards negative infinity in x and positive infinity in y. So this would be for a constant y. Now, of course, we could also talk about, and so again, this is a plane, so this is sort of shaded here. We could also talk about, well, what if we had more than one of these sort of important coordinate systems set at a fixed value? So maybe we also have our x set at a fixed value. Well, in that case, if we have x set, we're going to have an infinite plane that is parallel to our y-axis. And so you're going to hopefully able to visualize this a little bit better, because I know my drawings are a little hard to see. But if we have x and y fixed, the result is then going to be a line at the intersection of the two planes. So we would have an infinite line. And so this type of thing is going to become important later on as we're trying to visualize certain equations in our three-dimensional systems. But again, you can look more in section 2.5 if you want to get a better feel for some of these constant coordinate surfaces.